All right, so it looks like this is it for today. So here we go. So today what we're going to do is we're going to teach you how to code your robot to drive straight consistently. Once again, in case anybody's not familiar, this is our iDESIGN team. So I'm Dean Jack. I'm the in-house training expert. I also do Canada sales, and I also do support. We've got Andy and Mario, our co-founders. Sarah's with us today. She is the head of our marketing department. And then depending on which state you are, if you are in the United States of America, you'll notice that we have 3 US reps. We've got Scott, Brett, and or Steven. Whoops, the other way. There we go. Again, we are iDESIGN Solutions. VEX is our premier product, but we do have a full line of STEM solutions, everything from 3D printers, laser cutters, all the way through to software. So this is this year's challenge, pitching in. And as you can see, it's not a really complex game, but the hardest part is going to be making sure that the robot is in the exact right spot. Because you've got to have that robot in the right spot to be able to pick up the balls, but you're also going to have it in the right spot if you're planning on shooting the balls into the high goal. So this year is all going to be about having that robot in that perfect position every single time. So that is what we are going to do today. And that's the end of my PowerPoint because I know you guys love them so much. And we are now going to switch over to VEX Code and go live. But before we do that, I'm just going to switch cameras here and I'm going to show you what we are working on. All right, so this is my handy dandy robot cam. You'll see I've got my robot here. So I'm going to set it up perfectly straight. I am going to load my latest code. I'm going to let the gyro get ready. And what we've got is we've got a robot that drives nice and straight. But what happens when it hits something? As you can see, we can code this robot so that no matter what happens, it'll straighten itself out and keep going in the right direction. Now, obviously, that's pretty exaggerated with me giving it such a tug, but that's just to show you that the robot becomes self-correcting. So that's our goal for today, is to build an algorithm that's going to allow this robot to drive straight at all times, regardless of what it runs into, whether it's something physical or whether it's issues with the robot. Okay, here we go. Is everyone familiar with VEX Code? Everybody's used it? Yes, yes, yes. Okay, great. So the first thing I'm going to do, as always, I'm going to name this project. So I'm going to call it Dean's Gyro Drive. Just something simple, a file name I haven't used before, so I'm not overwriting anything. Again, this is being recorded, and I will be sending you a copy of this code once we have completed it, so you don't have to follow along or take notes about the code. My goal is to have fun teaching it and then send you all the information you need, including a copy of this recording, so you have everything ready to go. So the very first thing we need to do is we need to set up our robot, and we're not going to use the standard drivetrain. And the reason for that is we need to be able to steer our robot. So picture yourself, you're driving down the road. Your eyes are the sensor, and whether it's the wind coming up or whether the road turns, you're going to use that steering wheel and you're going to constantly adjust side to side. Now on our robot, we don't have a steering wheel. We don't actually have steering. So how do we turn our robot? Does somebody have an answer? How do we actually get our robot to turn? Right, so it's
control the motors.
Right, we control the motors left side and right side. So if we slow down the left motor, which way is the robot going to turn?
To the left.
Right, and if we slow down the right motor, to the right, and vice versa. If we speed up the left motor, it'll turn right. So that's how we're going to control the motor. So rather than using a drivetrain, what we're going to do is we're going to set up motors. So I've got the left motor in port 1. And if I can spell it, there we go. And I have got the right motor in port 6. Now, I'm not sure if you're aware, but when we build these robots and when we have the motors set up on, the motors are actually set up back to back, which means that in order for this robot to drive forward, we actually have to reverse one of the motors, and it's the right side motor. So I'm going to click the reverse button here, which now changes forward to clockwise on the right side. Now that's important for two reasons. One, just so you have an understanding that these motors do rotate differently. Second of all, if you have any experience with DC motors, you'll know that no DC motor runs at the same speed in forward and reverse. It is always a little bit different. So right away, if we've got a left motor turning the regular way and the right motor reverse, the robot will always stray a little bit, even though VEX uses good quality motors. So we've already got an issue even before we get started. The next thing I'm going to add, of course, is the gyro, and we add it manually because we're not using a drivetrain. And I am also going to add a touch LED just so I can use that to start my code. All right, so now that we've got our robot set up, and again, if you're working with the students, they should set up all their devices right from the start, and that way everything is set up. And then what I recommend is saving the file, and now they've got their template that's ready to control everything on their robot. So the very first thing I want to do is I want to calibrate the gyro. So as soon as my code starts, and I can blow this up so we can all see it, is that better? All right, so I want to calibrate the gyro. Now what that means is before the students start this piece of code, they've got to make sure that robot is lined up perfectly. And then what's going to happen is it's going to calibrate that gyro to the position where they've set their robot up. The next thing I'm going to need is I'm going to need a variable to control the distance of how far we're turning these motors. So I'm going to go to variables and I'm going to put in make a variable and I'm going to call it distance. So now we have a variable. So set distance to, this is going to allow us to set how far we want the robot to drive. Now, the next thing we need to do is we need to be able to control the motors. So we need to be able to measure how far the robot's gone and know if we've completed our distance. And for that, what we're going to do is we are going to use a while loop. So a while loop says while whatever condition we put in here is true, because robots don't talk in yes or no, it's true or false, while this is true. So what we're going to do is we're going to go to operators and we are going to use a less than. And what we're going to do is we're going to go to variables and we're going to say while the distance is, distance goes here, while the left motor, and you could use the left motor or the right motor, it really doesn't matter. But while the left motor position in degrees, so we're going to measure the left motor as it starts turning. While the left motor position in degrees is less than the distance that we've set, we are going to spin the left motor forward and spin the right motor forward. Once we've reached our distance, we are going to stop both the motors. So distance in degrees, and you can do this in degrees, you can do this in turns, your students can do it any way they want. There's no right way or wrong way, as long as they're using this type of format. So I'm going to set the distance to 360 degrees, which would be 1 full revolution. So our code says calibrate the gyro. So the code is going to wait 2 seconds while the gyro calibrates. Then we're going to set our distance, and this is what the students would change. So we're going to set it to 360 degrees. And then while the left motor position is less than the distance, 360 degrees. So while the left motor has not yet turned 360 degrees, we're going to spin the motors to drive forward. Once the left motor has moved 360 degrees, then we're going to stop them. So I'm going to plug this into my robot now. I'll move it up so it's a little easier to see, straighten it out. I'm going to download this code and I'm going to click run. And there it goes. It now drives forward 360 degrees, which is 1 turn. And these VEX tires are 200 millimeters or 8 inches circumference. So that's how far it has driven. Does everybody understand that concept so far? If you have questions, now's the time. Yep, absolutely.
Is distance always in degrees?
You can only do it in degrees or turns. Now, that being said, I will also send you code where you can do it in millimeters or inches. It's just a matter of adding some math to it. So we know that one turn is everybody here from the US? I should ask that first. Is there anybody here not from the US? Yes? Okay. So whether you're doing inches or millimeters, you can just do simple math. So one revolution would make this robot drive 8 inches. So if we do, 360 degrees. So if we wanted to go 4 inches, we would do 180. So it's math that they can do, or it can be added into the code.
And those are the regular tires, right? Not the omnidirectional.
That's right. The omnidirectional tires are also 200 millimeters, so it does work well for both. They're both the same.
I thought that was bigger. Okay. Can I ask another question?
Always.
And this may have been explained previously, but my brain's not there yet. You have the left motor going forward, but the right motor, I thought was reversed, but you already fixed that in the setup. Is that right?
That's right. I fixed it in the setup so that it's easier in the code. So if I didn't fix it when I was doing in the device manager, then I would have to do spin the right motor reverse, but then it would get confusing, especially for students, about which way the robot's going.
And you had mentioned previously that going forward is always a little bit faster than going in reverse for motors, right?
That is correct.
Does that mean that when we were driving it as a drivetrain before, like that when drivers are driving, they actually had to make one motor work a little faster because it was always in reverse?
For the most part, yes. The motors, now it's not a whole lot of a difference. It's usually 1 or 2%, but over a longer distance, every single VEX robot, if we just put in spin left motor forward, spin right motor forward, and just let them go, the robot would slowly start to curve. Absolutely.
That's where the gyro comes in because it adjusts for that. Yes.
Right.
Got it. Thank you.
Okay. Are there any other questions before we move on? Okay. So now what we're going to do is we're going to start using the gyro. And the way we use the gyro is we use the gyro to measure how far off course we are. So, and then what we can do is measure it. So we need another variable, and I'm going to make a variable and I'm going to call it error. So this is how far we are off course. All right. And I'm going to bring it in here. So this while is a loop that just goes round and round and round until we reach the final distance. But what I'm going to do is I'm going to change this to error, set the error to, where is my gyro? Gyro rotation in degrees. Now, if I take my robot here and I go to the device manager, which I've taught you about in other ways. So now I've got my gyro. If I turn to the left, the numbers are positive. If I turn to the right, the numbers are negative. Is that correct? Yes. So that's just something to keep in mind. So that's how it's going to help us with steering. If the robot's going to the left, the numbers go positive. So we're going to need to subtract them from the right side. And if we go to the right, we're going to add them. So what we're going to do now is we are going to go up to motion and we are going to set left motor velocity and we're going to set right motor velocity. And we need to do a little bit of math here. So for now, we can just use, no, we need to add speed. Sorry, I need another variable. And that is going to be speed. What speed our robot is going to be running at. So we're going to set the distance and we're going to set the speed. And we're going to set the speed to 50% just because my desk is small. Obviously, the students should start around 50% and work their way up once they get working with this code. Now we're going to use some operators. And I need a plus for the left side and I need a minus for the right side. And now if I go back to my variables, what I'm going to do is I'm going to take speed. Whoops, that didn't work well. I lost it. So what we're going to do is we're going to change the speed of this robot. So if the robot is going exactly straight, the speed will be at 50%. If the robot starts veering off on the left side, we're going to add the error. On the right side, we are going to subtract the error. And that is what's going to give us our gyro code. So let me download this. And hopefully you can all see my camera. I'm sure it's pretty small, but if I run this code now, you'll see I should probably change my distance a little bit more. I'll double that up. You can now see that if I run this code and I move the robot manually, we now have code where the robot will automatically adapt and head back to the proper heading. And that's simply by using the speed and the error to make a mathematical calculation of the robot speed. Now, you'll notice that right now the robot did not react as quick as it did when I did my demo. Did everybody notice that? So there is an issue where we need to add something, and in technical terms, it's called the KP. KP is proportional control value, but basically it's a number that we need to multiply the error by in order to get to fine tune it. Now, if we multiply the error by too much, what'll happen is the robot will actually duck walk. It'll overcorrect and it'll just walk back, forth, back, forth, back, forth the whole way. If it's too low, we get a robot that kind of meanders. It'll kind of go off course and correct and back and forth. So the KP students will need to do some fine tuning. So I'm going to make a new variable called KP. And what I'm going to do, again, we set up all our variables in the beginning. We set the KP up, and I have found that at 50%, 2 works very well. At 100%, 4 seems to work very well. So those are your baselines, and then the students can fine tune. It's also going to depend on their robot design, whether they're using omni wheels, whether they're using rubber tires, the width of the robot, etc. But that's just something that they'll need to figure out. Once they've got that number down pat, it's going to work great. And then what we need to do is we need to add some extra math. And what we do is we figure out what our error is, and we multiply that by our KP. So we're taking our error, and then in this case, we're multiplying it by 2. So whatever speed we need to change, we're going to multiply that by 2, just so the robot responds quicker. I know you're all excellent math teachers, so this should be no problem. Okay, so now does everybody understand the basics of this equation that we have built, this algorithm? And I will just do a demo here just to show you that now the robot responds much quicker. So again, I can set this to 4, download it again, run. And you can see that one didn't really work very well. We'll try that again. Tap it the other way. That at 4, it doesn't really respond well at all, and I have no idea why. We'll go back to 2. Run. And there we go. It works perfectly. So again, there is a lot of fine tuning there, but the numbers that I've gotten from a lot of the teams is they use 2 at 50%, 1 at 25%, and 4 at 100%. And that seems to work very well for correcting it. All right. Are there any questions so far?
I have one question. When I was here at the beginning, you set up the speed 360, and I was thinking it's just the degrees. I think Akiko was thinking this way also. Is that millimeters, centimeters? That's how you work, yes?
So it's actually just in degrees right now. I will get to the point where we do convert it to inches and millimeters later on. We just do some simple math.
Since I was thinking if it's degrees 360, when you told 360, I was thinking so the robot is gonna make.
No. So it's how many degrees the motor, oh, sorry, camera's over here. How many degrees the wheel turns, because the wheel's hooked directly to the motor. So it would be one full rotation of the wheel.
Okay, I see. Mhm. So now when it's 720, then it's.
2 rotations of the wheel.
Okay, another question, the speed. Is there any difference between when we put the speed on 50 or 70 or 100? So do you recommend the speed to be slower or faster?
I usually prefer that the speed, especially because it's timed, students are going to want to get it as close to 100% as they can, unless it's where they're either in a tight space or where they're moving up to an obstacle. They may want to slow it down a little bit. But generally, I recommend that students test code at 50% because it's a little easier, but then they're going to want to move it up to 100% because the farther they can get the robot going, the better they can do, the more points they're going to make. So the goal is to get it up to 100%.
Thank you.
No problem. Okay, so, yep, go ahead.
All of this, for me, like this is actually, very daunting, but, I have to let it soak. And I still don't really understand how just naming a variable speed allows the program to know what speed means, but that's okay. I'll get over that.
No, I can explain that. That's okay. So it's down here where we actually set the speed. So set left motor velocity 2 is saying set the motor speed. And then what we're saying is set the motor velocity to the speed, which in this case is 50%, plus the error. So hopefully the error is 0. So 50 plus 0 is still 50. And then, oh, I made a mistake here. That's why it's going the wrong way. I apologize. Let me fix this up. I put the KP in the wrong place. Speed minus the error. So we're actually setting the speed with these 2 blocks here. And that's how we control the robot. This should have gone here where we're multiplying the error. So my apologies. So let me go through the code once more. So these variables here are where we're telling the program what we want to do. So we want to move the robot, we want to turn the motor 720 degrees, which would be the equivalent of 16 inches, because we know that 360 degrees or 1 revolution is 4 inches or 200 millimeters. We want to set the speed to 50%, and then the KP is our multiplier for the arrow. So while the robot has not yet reached its destination or its distance, we're measuring the gyro and we're multiplying it by 2. So if it's off, let's say it's off by 4 degrees, our error now is 8. So then we set the speed. So our speed for the left motor would be 50 plus 8 would be 58. Our speed for the right motor would be 50 minus 8, which would be 42, in which case this robot is going to turn to the right until it gets back on course and that gyro rotation goes back to 0. So what we're doing is we're just using the variables to hold the values, and then it's these 2 lines here, the set left motor, set right motor, is where we're actually steering the robot. But this is a loop that's constantly going, so it's constantly reading that gyro and saying, what's the gyro at? What's the gyro at? What's the gyro at? And if the gyro is anything other than 0, it's going to change the speed on the left and right motor to get that robot back on course. Does that make sense?
So I'm just imagining, and our teams at my school, we've never used the gyro before. And so what I'm looking at is so far to get this weight, you said 1 rotation is about not 8 millimeters. What did you say?
8 inches.
Oh, 8 inches.
Sorry, 1 rotation is 4 inches.
1 rotation is 4 inches, 4 inches.
Correct.
Okay. And so to get this robot to go 8 inches forward, it's this huge code, right? And so what I'm wondering is, there's certain points where I imagine you can just duplicate it and just plug it into, because this is just to go 4 inches forward. And then they
Correct.
have to turn and they might want to go 8 inches
Right.
forward and then, okay. But there are some things that I think after they set up, I imagine it's a little bit more, it goes faster.
Yes, so this is, does everybody have an understanding of this code? Because that is a perfect segue into what we're going to do next, where we're going to actually turn this into a subroutine and make it much easier. So everybody understands how this code works and what it does? Somewhat? Okay, so now, as you mentioned, the students are not going to be able to sit there and copy paste, copy paste, copy paste. This thing is going to be 32 pages long by the time they're done. So what we need to do is we need to give them an easy way to be able to code this. Let me just get my right cheat sheet ready so I put everything in the right place. So what we're actually going to do is we're going to build a subroutine or a my block. So I'm going to go and I'm going to click on make a block, and I'm going to call this drive with gyro. They can call it anything they want. And I am going to add 1, 2, 3, 4, our 4 numbers. So the first one is distance. The second one is heading. The third one is speed. And the last one is KP. And that is going to give us this new block here, which is the block that the students are actually going to use when they want to drive the robot. So we now have to modify this. So I'm going to move this over to here, get rid of these. Now our distance becomes our distance variable. Our KP becomes our KP. Our speed becomes our speed. So I just subbed out variables. And the way this now works is when your students want to use this driving, and this, you can hide this off screen, you can hide this anywhere. So this is something where the students are going to be able to just pull out one block and how far they want to go. So we can put our 720 in here, our heading 0, our speed 50, and our KP 2. And you can modify the blocks over in the menu as well. So if you wanted, you could have this set up where you've already got your heading, you've already got your speed, and you've already got your KP in it. And now when they drag out that block, they really just need to change how far they want the robot to drive. And I will show you how this works. We're going to download it.
Dean, before you play that, what is heading? What is that referring to?
Oh, heading refers to what direction the robot's going. So it's a static heading. So straight ahead is always 0. It's like a compass. It's the gyro heading. So if we wanted to turn left, that would be 90 degrees. If we wanted to turn right, it would be negative 90 degrees. And I'll show you that in just a second. So let's make sure this works first. And as you can see, it works. The robot still drives properly and it still resets on its own. So what we've done though is we built this subroutine, which we can leave out of the way. And now the students, when they want to drive, they just have to plug in how far they want to go and their numbers into this one single block wherever they want to drive. So this needs to stay in the code, but it's not something that they need to work with. Now they can put their driving with the gyro, their arm going up, their arm going down, whatever their intake system. But when they want to drive, they just need to put this one block. And I usually put comments above. So what I would do in this case, just so that they remember, is distance, heading, speed, KP. Well, it should be small. So again, if they want to change the speed, they can change this to 100. We can download. And now it does it at full speed. So this is the block they'll use in their code when they're programming their actual autonomous. Does that make sense?
When you set it to 100, it has that kick in the beginning, right? It kind of like.
That's right.
But when you said it's 100, the KP should be 4.
Yes.
Does that help with the kick or no?
It doesn't help with the kick, but it definitely helps it correct from the kick. So one of the big problems that some of your students will know, especially if they're working with the rubber tires, is that when it takes off, it usually kicks and it usually goes off on a little bit of an angle. Whereas now you'll notice it goes straight because it corrects itself instantly.
Another question. I noticed that you are using a cable to code, yes? From
Yes.
robot to your computer.
That's
Last time
right.
we were talking about the control and that radio that is blue, and I checked ours was blue. And you said it's going to be wireless coding? Maybe
Yes, but only if you've got iPads or Android devices.
only if I have iPad or Android devices. Okay.
Right. Yeah, unfortunately with computer, they're still talking about it. VEX is saying they are working on wireless coding from PC, but they do not have that working as of yet.
Okay, thank you.
So that's why, yeah, that's why you see me working with the cable. I usually just leave it connected, so I'm not plugging it in and out. But again, I'm not on the field. I'm just working in a nice small space. All right.
So Dean, I'm sorry, one more question. And this is very basic and I apologize other coaches for this, but I noticed like when you have that one where you have the defined drive with gyro distance, you know, that thing off to the right, it doesn't actually have to be attached to the when started column in order for it to influence it. Is that right? Like you're setting the define off to the
Right.
side.
Yes. So this is defining what this block will do. And then the actual block is this block here that we need to connect.
So they kind of know that each other is there.
That's right. So this block knows when this block runs, it says, go over to this and run this code using these values.
So you can't have the drive with gyro block without having that other definition set.
That's right. Yeah, it won't actually show up. There is no drive with gyro block until you make your define block.
I see. Okay, thank you.
No problem. Yeah, so this, again, once this is working, students can move it. I mean, we do have a little bit of a canvas here. They can move it out of the way and, whoops, that's not what I need. And not even see it as they're coding. As long as it's on the canvas somewhere, it does not need, whoops. I hope control, there we go. Control Z does work, by the way, in VEX IQ blocks, just in case you accidentally delete something. Control Z will bring it back like I just did in that case. Okay, so now again, so if the students were coding, they just keep coding here. And when it's time to drive again, they go down to my blocks, they just bring out another drive with gyro and they can put in the values. I don't know why I lost my values. So I usually make sure my heading is set at 0, speed, whatever their default's gonna be, KP, etc. So the last thing we need to do, well, not the last thing, but the next thing we need to do is we need to be able to use this code to turn the robot as well. So we've already put in heading. So again, we're gonna use a little bit of math. I'm gonna use the minus. And I need to put that inside with the heading. Oops. Got to grab the right parts of that. So what this is going to do now is it is actually going to allow us to use a heading, which means if I change this to 90, this will do a lot more than just having the robot drive straight. Let me set it up where you can see it. I'm going to pull it this way a little bit. And now when they want to, whoops, wrong way. All right, one sec. Let's check my sheets, see what I did wrong. I think it's the KP. Let me just pull that out. Run it. Give me 1 second, set the error to the heading. I did test this all out, rotation in degrees. And it did work. I just got to figure out. Oh, that's what I did. All right. You know what? I'm going to load this in. It's a lot easier. I know it works. So give me 1 second. Experiencing technical difficulties. And this is why I'm going to send you the code, is to make sure it actually works. Just got to reboot it. There we go. All right. Let me share it again. There we go. Okay, so now I've downloaded that. And what you'll see is I've added lines to this code. So we've got to drive forward. If we want to drive reverse, we set the speed to negative and drive straight, except I'm missing the bottom half of this. Bear with me. Stop. I don't have the reverse in this one yet. So as you can see, it probably drove off the screen a little. I'll reset it here and run it again. But what we now have the ability to do is we can not only drive, but we can drive and do our turns. So what we're doing there is the robot is turning 90 degrees to the right and then still using that gyro to drive as far as we want. So it's not just driving forward, it's driving and turning and driving some more, all in one lineup. That's why we've got the heading in there. So you'll notice here, I'm driving for 1,000. My heading is -90. Speed is 50. And in this case, my KP is 1. I can change that to 2. It'll be a little more responsive. And run. So what we built is we built them a complete, the students will now have a complete algorithm where they can now code the robot to go exactly where it wants and in any direction. Now, if for their next drive straight, so we go to my blocks, drive straight, if they wanted to keep turning to the right, they could go -180, -270. If they want to turn back the other way, then they can go 0 or 90, etc. So it's a little difficult for them to understand, but what that actually means is this is 0, this is -90, this is -180, this is -270, but then they can also turn the opposite way where they can go 90, 180, or 270. So it does work both ways, whether they want to get there by turning left or by turning right, depends whether they want to use a negative numbers to the right and a positive numbers to the left. So it might help to make them up a little cheat sheet, just showing them because it's going to be based off the orientation of where the robot starts. So if you set that right behind where they're setting their robot up, that's their sheet. So it's no longer turn right 45 degrees, it would be turn to 45 degrees, turn to 90 degrees.
I have one question, if I can interrupt you.
Of course.
Here in Slovenia, if we turn right is positive, if we turn left is negative.
Okay, so that may have to do with the way you set up your heading.
Yeah, probably on settings.
Yes.
And change reverse.
Yeah. So again, you may find that, yes, exactly. You may find that, you know, my numbers are backwards and 90 degrees is left. As long as, you know, test it first with the students, or have the students test it, have them make up their little cheat sheet. And then once they've got this algorithm working, it's not going to change.
Okay, thank you.
All right. So the next thing I'm going to show you is the final code. And this is the one I'll send you 2 different versions.
Wait, before you move on, Dean, I'm so sorry.
That's okay.
I don't know what to call that group of, what is it called? Drive, gyro, no, I can't see it. You know, the things that you have off to the right?
This
You
one.
call Yes, I don't know what to call that That
That's
whole,
it's in Scratch, it's called my block, or in computer programming, it's called the subroutine.
okay, the subroutine, I like that. All right.
Yeah.
So for the subroutine, is that something that needs to be changed constantly, or could it be as simple as once you set up your subroutine, it's good to go no matter what you want to do?
That's exactly it. Once they've fine-tuned their subroutine, they shouldn't really have to change the subroutine at all. The only thing they should be playing with is basically their data over here, which would be their speed and their KP. Once
Okay.
they've got that fine-tuned for the robot, once your team says, you know what, at 50%, our magic number is 2.3, at 100%, our magic number is 4, that's all they should do. And now they should be able to code this robot to get anywhere on the field that it needs to go.
Oh, see, I wouldn't even know if I would know or my team would know what the magic, like what the magic number would be. Like,
Well, and again, that's what I mentioned. If the robot tends to meander,
Mhm.
if it's wandering, if it's kind of correcting, so it's more of an arc where it gets off and it's kind of wandering back and forth,
Instead
then
of snapping.
the KP is too low. Yes.
Oh,
If-
I see, I see.
If it's doing the duck walk, where it's quack, 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 and the butt seems to be shaken, the KP is too high, so it's overcorrecting.
Oh,
If you don't have either of those, you're in the sweet spot.
okay, thank you. That's language I understand. Good. Thank
All
you.
right. So I am going to start with the final code. I'll do inches first, and then I'll show the metric. So what I've done here is you'll notice this code gets a little bit longer. I got to shrink it down a little bit. Actually, what I'll do is I'll blow it up and I'll go through it. So this is the code that we've just used, the middle section here. All right. So the first thing we need to do is set our positions to 0, because every time we run this, we need to reset our motor position, right? We need to reset our counter for how far we've driven. All right, this is our drive straight block. Then we're going to convert to, in this case, inches. So what we're going to do is we're going to take our distance and multiply it by 45. So if you want to go 1 inch, you would need to turn the motor 45 degrees. So now students, when they're using this block, their drive straight, 8 inches, 7.2 inches, 4.3. This is actually in inches now to make it easy for them. Heading is still heading, speed is speed, and then there's the KP. But what we're doing is just simple math so that they can code it in inches instead of in degrees. So we're converting degrees to inches, knowing that 45 degrees equals 1 inch because 4 inches is 360 degrees.
And one question, sorry, if you use millimeters, then you don't need to convert, or
Yeah, I did the conversion to centimeters actually, but yes, you still need to convert because 360 degrees equals 200 millimeters.
actually it's on wheels.
Yes, that's right,
I think.
Exactly. It's written right
Yeah.
on the wheels, 200 millimeters, yes.
Yeah, okay.
So you can convert. So then we need to know whether we're going forward or going backwards. And the reason we need different routines is if we're going backwards, the encoders, the counters are actually counting negative. So all we needed to change in the code, if we're going to go backwards, is we change it to a greater than instead of a less than. So that's why this code does look so long. And what I've done is I've changed the code so that it reads the left and the right motor position, not just the left. So it's going to be more accurate. It's whichever one gets there first. So instead of while left motor position in degrees is less than distance, I added in the or block. So I said while the left motor or the right motor is less than the full distance. It's just going to make things a little bit more, what's the word I'm looking for? It's going to be a lot more accurate. Yeah, precise. All right. And then this, again, the same code. We check our error, our heading minus our gyro times our KP. We set our left motor and right motor speed, and we drive forward. Going backwards, again, looks exactly the same. I don't know why it won't let me move this over further. The only difference is we use a less than sign because we're going negative. So So I can shrink this down. So this is the final code that your students will use. And again, they should not need to make any changes to this actual subroutine. This should work for them regardless. And now it's just a matter of driving forward, driving backwards. And to drive backwards, they just change the speed to a negative number. Let me dive in. Whoops, going the wrong way, Dean. All right, there we go. So to go backwards, they just change the speed to a negative number. So if I download this, put it in the robot, run it, it's going to drive forward 8 inches, back 8 inches, and then it's going to turn to the right and drive off my desk. It'll drive 12 inches. So this is now how they can not only drive straight, but also control all their turns with one piece of code. Are there any questions about this before I switch over and just show the metric?
My question is I noticed that your subroutine is, you started off with a smaller subroutine and then you kind of added to it.
Yes,
That's just to take us through the steps, right?
that's right. Exactly.
Okay.
Just to explain the
So we
steps.
understand why you built it. Okay.
That's
But
right.
for our kids, and again, I don't think I'll ever be able to explain to them everything
Well,
that you just
I've
said.
got great news for you. At the very end of this, I'm going to send you a link for an 11-minute video where a young girl explains this code, how it works, and builds it right in front of you to
Oh,
show
thank
your
God.
team.
Okay. Good.
So you don't have to teach this to your team. I just wanted to go through it slowly so that you had a better understanding if your team has questions.
Thank you.
No problem. All right. So I'm now going to open up the millimeter one, which is actually centimeters. And again, it looks identical. The only difference is we take the set distance in millimeters and we multiply it by 18. So what we're doing is we're converting it to centimeters. So you can see here, drive forward for 30 centimeters, drive backwards for 30 centimeters, turn right and drive for 45. And I can do that one. I actually can do that one sideways. It works better. And there we go. So once again, they shouldn't have to do any work with the actual my block, as long as they have a good understanding of how it works. Really, all they will need to do is just put in how far, and in this case, it's in centimeters, what heading they want to be on, again, the speed and the KP, which should be 2 for this robot. So this, again, will take a little bit more time to set up and to test once they've got their robot built. But then once they've figured out what KP works with what speed for their robot, it should be as simple as putting these numbers in. And what they're going to find is that the consistency should always be there. Are there any questions? And again, I will send you the metric and the imperial so that you have both. You can use either. Really, the only difference is this one block here where we just do some math. And that should actually be distance in centimeters. I switch it to centimeters because I know students have trouble with millimeters when it's, 200 millimeters is 4 inches. So it's easier to do 20 centimeters, etc. And especially when they're measuring, there's not too many tape measures that are in millimeters. All right. So I always like to give credit where credit is due. And I have used this code before in Java, but I'd never seen it in blocks. And fortunately for us, Caution Tape Robotics, which is one of the world-class teams, actually, I'll show you a little bit about them. These are the highlights of their previous season. You can see that they set new world records and they did quite well at Worlds. So this is one of those teams where everybody says, how do you do your autonomous so well that you can keep setting world records? They're one of the top teams. And they actually made this tutorial on how to build to drive straight with the gyro. And you'll see that looks very, very similar to mine. That's because it is. They give you the actual code here, which I will actually send you so you don't have to build it yourself. But they also give you this great little video.
field can be uneven and wait
And there she
you
is.
have a simple
So this
piece
young lady will explain to
straight.
your
Why do we
team
need a piece straight?
why we need the logic, and she goes through it step by step, just the same as I have. She doesn't explain it in as much detail, but she goes through how to build the entire code. So this is the one you want to show your team. It's also only 11 minutes long. They're not going to want to sit through our 53 minutes, that's for sure. Okay, so I will send you a link to this. Again, there's also the video. You can pop it out in YouTube. So you can either show them the video or the web page or both. And this will definitely increase their reliability with their autonomous code. So at this point, are there any more questions? Yes.
So the gyro is really used primarily for getting your robot to go straight or in the direction that you want it to go and to correct itself.
Yes, absolutely.
And I think I read somewhere that it's best to have it located in the center of your robot. Like
So yes, the best place is in the center of the robot, and preferably 1 inch away from any motors or any other electronics, because it is a magnetic field that it reads.
Oh,
So if possible, kind of put it somewhere on its own.
okay. Because I noticed yours is towards the front. Is that considered center?
No,
Or like
this
center
is,
of mass?
no, this is the only reason it's there is because this is the VEX autopilot build that I work with, and that's where VEX put it. If I was building this robot, I certainly would not put it there. I would definitely try to find someplace a little bit more centered, probably a little, and away from other things.
Thank you.
No problem.
This was great. I have to digest.
Again, and that's why we recorded it. That's why I'm going to send you out the code that you can put into any robot, as long as the motor, especially if it's a VEX build, the robot will be hooked up to 1 and 6. If it's not, all you need to do is go in and change which one of the ports you're hooked up in with the software. You should be able to put this in any robot and test it out. And that's the goal. And then from there, show the students, show them the video, make sure they have a basic understanding of how it works. That way they'll be able to troubleshoot. And from there, once they've got their competition robot built, they can put this code in, fine tune it with the KP, and then they should simply just be using that My block for all of their driving, forward, backwards, and all their turns. And they should find it very, very consistent.
Thank you so much.
No problem. So are there any more questions before we end?
Do you think as a beginner team, and when I say beginner, we've had our team for a few years, but we have a whole new set of kids every year for the most part. And so it's like, Groundhog Day, like we start over all again. Do you recommend that they start with a drivetrain and then switch over to this once they understand how coding kind of works? Or like what
So
do you think would be?
do you start with all new students, or do you still have some from last year?
No, I have all new students.
Oh, ouch. So I've always been lucky where I have succession. So I teach the first year, and then they teach the next year, and then they teach the next year, because I've always got a range. I would certainly start with drivetrain, because it's going to be much easier for them to understand and get them coding drive forward, drive, back, turn left, turn right. That'll give them that basic understanding. And then once they have that, they're going to automatically say, hey, how come my robot doesn't end up in the same place every time? And then you can explain to them. I mean, the video does a great job here. You can actually just play the video for them. And she explains in the beginning why robots, start to meander. She talks about the motors heating up. She talks about why does it always work at the shop or at the class and never work on competition day? And then leads into, this is what they use for repeatability. And then, you want to create that need. If you give them this right off the bat, they're not really going to understand why they need so much coding to be able to do it. But once they've coded it a little bit and realize, hey, we've got an issue, then it's a great time. One other thing I should mention, I know I mentioned it when I talk about the VEX hardware, and that is the batteries. If you're doing any type of autonomous, make sure your batteries are above 80%. Because if they're not, what happens is your sensor readings are off, the motor values are off. So always make sure that the batteries are charged more than 80%. And what you'll find is if you charge your batteries, pull them off the charger, let them cool for a half hour and plug them in again, they will charge up some more. They will charge up to 100%. So I always double charge my batteries before competition.
Okay.
But between the battery maintenance schedule and this code, your team should have a much higher rate of success with the autonomous coding.
One more question.
Yes.
What is your suggestion to start the coding after when we built the entire robot? Or because I'm thinking if we change anything on the robot toward the end, it may not work well. Am I correct or no? That was my experience.
Right. So I've always started by having the students build not necessarily this, but some sort of drivetrain, especially if you're starting over, even if they just build the base drivetrain, which is basically just the robot that'll drive, have them put a gyro sensor on it. Just in the center up there is fine if it's by itself. And I usually teach them the basics of coding. So set up a little maze, drive forward, turn left, turn right, or you can do it on the VEX field. You can put some things in and get them used to coding the robot from getting from just point A to point B. The idea with this code is that it's designed in a way that even if they make changes to their robot, because it's actually measuring, the robot should still be very consistent. Yes.
But if our kids have been, if they start off working with the virtual VEX VR, is there a need for them to still build a little basic bot?
No, if you're going to start with the VEX VR, it's perfect. That's a great way to start. So then you don't have to waste the time building the basic bot. You can get them to build whatever you're going to use, whether it's the hero bot or whether, whatever build you start with. And get them building that. So yes, you can start them with the VEX VR. They're going to learn about getting the robot where it wants, and then they can build their robot and then move to the coding of that.
Because Alita and I are at we're a school team. And so we don't have the luxury of meeting for hours on end for multiple times a week. And so we have very limited time to meet. We volunteer, right, to do this. So
yeah, no, I completely understand. I ran my club as a volunteer. We only met for 2 hours a week. So it was a challenge when we went to competition and we met, we used to compete against caution tape. So
oh my gosh.
Yeah.
Wow.
And I mean, they work on their robot 5 days a week. The one thing I will say is they're an incredibly gracious team. They would always spend time talking to my teams and helping them out. But it was one of those things where we would have meetings and, we would say, do you want to meet more? I was fortunate enough to have a workspace that was donated where we had access to it 24/7. So I did have some teams that would come in on a Friday night or a Saturday and program and work on their robot. But for the most part, we didn't have enough time to perform at that level. But as long as the students understand that and the expectation is set that we're not going to end up going to Worlds, they understand that. And our goal was always just to get to provincials. Then, the kids had a great time and they still learn just as much. But you're right, with a shorter time span, you have to really modify the program. So yeah, I would probably give them VEX VR as homework, right? I would start off doing a class where I would show them this is how it works and then give them the maze as homework, give them other ones as homework so that they're coding on their own time. And then when it comes to getting to the robot, then yeah, get a robot built, get it working well with the controller and then start coding it.
Thank you.
No problem. So do we have any more questions?
Time for lunch. This has been great. Thank you so much, really.
No problem. And as I mentioned, I understand this is kind of like rocket science. So I do offer support. So if during, if you get through this, you still got the video, you've got the resources and you still have questions, by all means, please reach out to me. I'm more than happy to help you. If your team's having any issues, you can reach out to me and I'll do what I can to help. So, don't be shy. Feel free to reach out and just send me an email. We can do a quick video meeting, or sometimes I can just, work on the code a little bit, send it back to you, etc.
Thank you.
Thank you. Thank you.
No problem. All right. If that's everything, then thanks very much for joining me today and have a great day.
Same to you.
All right. Thanks.
Bye now.
Thank you so much. Bye-bye.
Thank
No.
you.
Bye-bye.
Bye bye. Thank you.